Okay, this is Chapter 2, Lecture 14, Improper Integrals. Before I say anything about them, let's look at an example. So let's take this function 1 over x squared and find the integral from 1 to a. And a is some point on the x-axis bigger than 1. So this, in fact, is this area. So this is this area here. Okay, let's find it. So this is 1 over x squared is in fact x to the power -2, so that is minus 1 over x from 1 to a, which is minus 1 over a plus 1. So it is 1 minus 1 over a. So this integral, this area is in fact a finite number. So this area here is 1 minus 1 over a. Now what happens as a gets larger and larger? As a gets larger and larger, which means a goes to infinite. So a comes here, then here, then here, and so on. Then the area gets larger and larger, right? When a gets larger, this denominator gets larger, so 1 over a gets smaller, so 1 minus 1 over a gets larger. But what is the limit? Which means as a goes to infinity, I am finding this area under this curve from 1 to infinity. So one side of this is, say, unbounded. So from one side, this area has no bound, just goes to infinity. If this side is bounded, this to the left, it's bounded. But what is it? So it is, say, natural to define the area under this curve from 1 to infinity to be the limit of this thing. So limit, so say 1 to infinity, that is this area, this unbounded area from one side, x squared dx. It is natural to define it to be the limit of this as a goes to infinity, which is 1 in fact. Okay? Well, at least the first time I saw this thing, it was amazing. It was maybe I can say that I really got interested in mathematics because of this thing here. This the idea that something which is unbounded has a finite area, and not just finite. Well, finite, there's no difference between 1 and 10 million. They are both finite, but it's 1. And but anyway, this kind of integral that represents some, say, unbounded area, because area is integral is area, right? So an unbounded area is called an improper integral. And this type, say, from some point, say from left or right, it's bounded. From one side, it's not bounded. So this one, for example, is defined to be this thing, in fact. So this is defined to be limit as a goes to infinity of integral from 1 to a, 1 over x squared dx. As I said, it's natural to say that this area, this unbounded, say, geometric object, the area of this unbounded geometric object, the areas are unbounded, but the area of this geometric object, which is not bounded from one side, is in fact limit of that as a goes to infinity, and we see that limit is a finite number 1. So area of an unbounded geometric object is finite, and that's amazing. In fact, if you look more carefully, you can feel the idea of limit here. It's in fact limit of something. Well, it's defined as a limit, but it is like you're adding small pieces, but the small pieces are so small and get smaller and smaller and smaller that in the end they are basically nothing. So basically it's like you're adding nothing. And it gets closer and closer and closer and closer and closer and closer to 1. So, but definitely we cannot draw this shape. Infinite doesn't mean, infinite shape, what they're talking about. So we cannot really draw a picture of that, but we can just imagine. It should be something in your imagination that as this gets larger and larger, the shape goes to the right. It has an area, and this area is in fact a finite number, which in our case is 1. Well, this type of integral, 1 over x squared, is crucial in, especially when it comes to studying infinite series. So let me look at this type of integral from 1 to infinity for any n here. So let's say if I have n here, so let's find this integral from 1. It can be from any point to infinite. So this one is not important. So let me, well, since I said it's not important, so let's write a, okay? So let's put a here and b here. It starts at point A, which is bigger than 0, and goes to point B, and b goes to infinity. So that is 1 over x to the power n dx. And let's assume that n is bigger than 0, okay? Let's assume n is bigger than 0, because if n is less than 0, I will have this goes up here, so I will have something like this: a to infinity x to the power 2, for example. And we know that is infinite, because the shape just goes way up there. But this one, 1 over xn, for n bigger than 0, has this kind of graph. So the graph goes to 0. As x goes to infinity, the graph approaches the x-axis. So this term goes to 0. But this one goes to infinite. So let's assume that n is bigger than 0. And I said this should be limit of, defined as limit of b going to infinity of integral from a to b of 1 over x to the power n dx. Now what is 1 over x n? Well, this is in fact x to the power negative n, right? So this is x to the power negative n. So the integral is the limit as b goes to infinity of x to the power negative n. What is it? Let me, how should I write this thing? So it is this. If n is not negative 1, if n is not 1, we have this 1 over negative n plus 1 x to the power negative n plus 1, and from a to b. If n is 1, then we have 1 over x dx, and that is ln of x. And since x is positive, I'm not using absolute value from a to b. Okay, so let's look at this. So what is this one? As b goes to infinity, that is, this one is in fact ln of b minus ln of a, and then I will write the limit here, limit as b goes to infinity of this thing, and the other one is, the other one will be 1 over 1 minus n times b to power 1 minus n minus a to power 1 minus n, right? So b to power 1 minus n, a to power 1 minus n, and now this one, ln of b is infinite. Now you might say, how do you know that? Oh, well, I know that. So this one is infinite. This is just a positive or negative, doesn't matter, because infinite is minus something or plus something, doesn't change anything. Let's look at this one. So what is this? Well, 1 minus n. So I have this expression, b to power 1 minus n as b goes to infinity. Let's look at this more carefully here. So I have to look at this limit. Limit of b to power 1 minus n as b goes to infinity. Okay? So what do you think? If n is, well, n is not 1. Okay, so well, I should have written something here that n is 1. Yeah. For this one, n is not 1. So this is when n is not 1, and this is when n is 1. Oh, okay. So we are looking at the case when n is not 1. So what happens? That is the limit of as b goes to infinity of sub. If n is bigger than 1, if n is bigger than 1, I write this thing as 1 over b n minus 1. The other case is b 1 minus n. This case is when n is bigger than 1, n is less than 1. So what happens? If n is bigger than 1, I have b to some positive power, right? B to some positive power. So as b goes to infinity, this is infinite, and 1 over infinity is 0. So I will get a 0 if n is bigger than 1. And this one, 1 minus n when n is less than 1 is a positive number. So it is b to some positive, say, exponent. And as b goes to infinity, this goes to infinity. That's like a large number to some positive exponent. That gets larger and larger and larger and larger. So this one goes to infinity when n is less than 1. Okay, so what can I say here? Let me erase this thing and write it here. So this one will be, well, let me, this will be, in that case n bigger than 1, this will be 0. So I will get 1 over 1 minus n times minus a to power 1 minus n when n is bigger than 1. And look, you might say, well, how come this is negative? No, it's not negative. 1 minus n is negative itself. So a negative here, they cancel out. We get a positive number. The other one is infinite when n is less than 1. and this case is n equal to 1. Okay? So we have some general formula for this type of integral. Let me erase this thing and write it down here for you. And so this integral from a to infinity, and let's say a is bigger than 0, of 1 over x to power n dx is infinite, or we can say it's undefined or divergent, say divergent if n is less than equal to 1. And well, it's all bigger than 0. And it's convergent. It's convergent, and I wrote down something. In fact, you can write that as the I can't remember. Was it 1 over 1 minus n times minus a to power 1 minus n? Is it? I guess so. When n is bigger than 1. Okay, so it's convergent. In fact, for us, the convergence is more important than what it is, because you can always, if I give you this from say 5 to infinity, you can find it without even looking at this formula. Okay, so we have this general form, which means what? Which means, for example, for 1 over x, for each one of them, no matter what n is, if n is bigger than 0, I will get something like this. So for all of them, we have this shape. If n is large, let's draw a picture here. So if this is for some n, this is for an n which is less than that. So if, for example, this is for n equals, say, 2, this one is for n equals, say, 10, right? 1 over x to power n. Why? So, and this is 0.1. All of them, they go to 0.1 here. This one, which is n to power, n is 10, that's x to power 10. And you can see that if when I go further and further, for example, at point, say 100 here, 100 to power 10 is 10 to power, say, 20. It has 20 zeros, so that's almost 0. So at about point 100, this is almost, it is touching the x-axis. It never intersects or touches, but let's say almost. But n equals 2, 100 to the power 2 is just 10,000. So this should be above this one. So as n gets larger and larger, that thing, I mean, this curve gets closer and closer to the x-axis much faster. And so the area under this one is much smaller than the area under the other one. And also the formula tells you that. So this is the shape when, and if n is, say, 1/2, for example. If n is 1/2, which is less than 1, then it looks like this. It goes like this. So n equals, say, 1/2. So no, it doesn't go up. So let me get rid of this 2 here. It never goes up. It always gets closer to 0, but not that fast. It goes down. So that's n equals, say, 1/2. It's amazing that, say, for this one, this area is not finite, but for this one, this area is finite. Although both of them, they approach 0, but one of them approaches 0 much faster than the other one. N equals 10 goes to 0, but n equals 1/2 just goes boom, 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 gets closer to 0, but the rate of getting close is much slower than n equals 10. So, but anyway, it's amazing that at n equals 1, which gives you ln, in fact, it is still infinite. Okay, another type is integrals that of the same function, 1 x to the power n. Now this time I'm going to find this integral, this area. The area to the left, this area. Let's find this area to the left, okay? So let's say this goes from A to B. Again, I let this point be, not B, A. Let's put it A because A is to the left. So from A to some point B, and A is close to 0. So I'm finding this area. Let's find this area and see what we get. So this one is, I want to find the integral from 0 to b 1 over xn dx. And this function is not defined at 0. In fact, this line, which is x equal to 0, or the y-axis, is a vertical asymptote for this function, for any n bigger than 0. So it approaches this and goes to infinite. So this is also infinite. This is an infinite, say, shape. That's an infinite geometric shape, unbounded, let's say. Infinite doesn't mean anything. It's an unbounded shape, but we are trying to find its area and see if the area of this infinite or unbounded shape is finite or infinite. So let's try this one. Well, the integral is the same again, so that is so let's write it as a limit as a goes to 0 plus, we are going this way, of integral from a to b 1 over x to the power n dx. So again, that is 1 over 1 minus n x to the power 1 minus n from a to b when n is not 1, and it is ln of x again when n is 1. So I'm finding limit of these two, so it's I forgot the limit. So it is in fact the limit of this. Limit from a to b as a goes to 0 plus. Okay? So let's see. This one, so it's again limit as a goes to 0 plus of this one will be 1 over 1 minus n times b to the power 1 minus n minus a to the power 1 minus n. And this one is ln of b minus ln of a. Okay? So what is this one? As a goes to 0, ln is not defined at 0. Okay, so this is undefined, or let's say infinite. Because it gets small, that's minus infinite. So this is infinite. How about this one? What happens to this one? So that is, this one is finite, that's a finite number. What happens to this one? So I have to find limit of this as a goes to 0. So let me erase this and try the other one and see what happens if a limit of a 1 minus n as a goes to 0. So again, I divide it in two. One is when n is bigger than 1 and n is less than 1. So n bigger than 1, I will get a n minus 1, n bigger than 1, and the other one is itself, 1 minus n, when n is less than 1. So if n is bigger than 1, n minus 1 is a positive number. So it will be 0 to positive number, to a positive power, so that's 1 over 0. So that one is, say, infinite. N is bigger than 1. How about this one? This one is n is less than 1, so 1 minus n is a positive number. So 0 to a positive number will give me 0 when n is less than 1. So we can say that this is infinite or undefined, or whatever you call it, when n is bigger than 1, and it is 1 over 1 minus n times b to power 1 minus n when n is less than 1. So it's divergent here, convergent here. So I have come up with some general idea about this integral, which gives me the area to the left, and that is, let me erase all these things and write it here. So this is infinite or divergent if n is bigger than 1 or equal to 1. You see, for Ln was also, and convergent when n is less than 1. Okay, so as you see, it is the opposite, which makes sense. It is the opposite of the other one. So let me draw some picture here for you and show it in picture. And so this is any point here, let's say point A or B, whatever. So this area, so this is 1 over x to power n. Okay? And if n is bigger than 1, this is finite, this is infinite. Okay? This area is infinite, this area is finite. Okay? So that is when n is bigger than 1. When n is less than 1, so 1 over xn, when n is less than 1, this is finite, and this is infinite. Okay? This is infinite. What happens to 1? 1 is like so bad in that sense. This is in fact 1 over x. 1 over x, just put this anywhere, infinite, infinite. So 1 over x from either side will give me infinite. Okay, now, you might say, what is the examples of this? Examples make more sense. So this one is something like 1 over x squared. It can be 1 over x, say 5. It can be 1 over x to power 1.2, etc. This one can be 1 over x to power square root of x. That is x to power 1/2, right? So whenever you see square root, or whatever, write it as exponent. It can be 1 over x to power, I don't know, 0.1, for example. It can be whatever. So the exponent should be a number less than 1. Right? If it is 0.99999, that's also okay. So that's also fine. So it shouldn't be exactly, well, 1 is that thing. So if this exponent gets close to 1, 0.9999, whatever, that's still okay. So these are examples, and as I said, be careful. You might see something like this, and don't get confused. This I say, gee, I cannot find this thing. Yeah, right. Always, 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 when you see a radical, write that radical as exponent. So it might be the third root. Well, so it was radical with I don't know what to say. Anyway, so third root, write it as x to power 1/3. Okay. Don't leave it like this, then don't make yourself confused. Okay, so these are examples of improper integrals, and as I said, we will use this thing when it comes to limits. I mean, infinite series. Let me see if there is anything. Yeah, so there's another nice theorem here. So I might have there might be a situation for which it is infinite from both sides, and that happens in, for example, when you're studying probability and density functions. So a density function is defined from minus infinity to plus infinity, and the area under the density function should be 1. So you might have something like this if it is density function of probability, say, and it might be, so it is like density function, which we call it PDF, probability density function, then it should be finite. From negative infinity to positive infinity should be finite. But how do we define this thing? We define it from both sides. So we say B or A to B as A goes to negative infinity and B goes to positive infinity. So you can write it both A and B, and then let's set A and B go to infinity, both of them. So that is a situation that it is from both sides. So we write it like this. We write it, say, from A, for example, to some point. So let's write it like this: limit as A goes to negative infinity of this thing, A to, let's assume that this is continuous, so it can be to point C, any point, and fx dx plus limit as b goes to infinity of integral from C to b fx dx. Okay. So we basically are saying that there's an A here, and C can be anywhere, C, and this is B, so B goes to infinity and A goes to negative infinity. Okay, so I'm assuming that this is continuous, so this point can be anywhere, so it can be 0. Depending on the situation, you might use 0, but it might make things much easier. But anyway, so this is the definition of an integral like this, which has, which is, say, improper from both sides. Okay, now, another type of function that you might see is e to power negative x and its family. So that is the type that also, you see, if a function you're finding, it goes from, say, A to, say, infinity, this area, for example, this area. If a function is like this and goes to 0, then there is a chance that this area is finite. Okay? And one of the functions that this happens to that function is e to power negative x, right? So e to power negative x from 0 on starts at 1 and then goes down close to 0. So this also will give me from, say, even from 0, because at 0 it is defined, but any point to infinity e to power minus x dx. So this is also convergent. I leave that to you to find it. In fact, that might be part of your homework. So any integral that involves e to power minus, say 2x minus something, or 1 over e to power x, for example, that's also e to power minus x. You can graph it and see if it goes to 0 as x goes to infinite. If that goes to 0, it's like this, the curve, the graph is like this, then there's a chance that this area is finite, although the shape is unbounded. Okay, so that is another one. When you have, this is in fact 1 over e to power x, right? So this is 1 over e to power x. The other one is 1 over x to power n, okay? So either you see something like this, with not necessarily e to power x, so it is of this family, e to power kx, for example, or you have x to power n. So these two, the family of these two, are in fact, you can study them, and this one, if k is positive, for example, then this is finite, the area is finite. If k is negative, then it's infinite. So there are different cases, but you can draw the graph and see for yourself if it goes down to 0, or you can just check. Find the limit. The limit of this function as x goes to infinity. This one and this one, both of them are 0. If k is positive, limit as x goes to infinity is 0. This one also, limit as x goes to infinity is 0. So the graph goes down like this. So there is a chance. There is a chance that the area from a to infinity is finite. Now we will see this phenomenon in infinite series. In fact, if it doesn't go to 0, if that function doesn't go to 0, if fx, limit of fx as x goes to infinity is not 0, then there is no chance that this integral is finite. In fact, we can prove that it is infinite. So that you will see that in infinite series in a different, say, context. So there is a comparison test, and this comparison test becomes interesting again. So this is a comparison test. It's important. Now, why is it important? Because sometimes we cannot find, or it's very hard to find an integral. So we use the comparison test. For example, can we find this thing easily, x to the power, say, 4 plus 1 dx from, say, 1 to infinity? No, it's not that easy. So, but do we have, is it convergent or divergent? So, comparison test, in fact, is about convergence or divergence. It doesn't give us the integral, it just tells us whether it is convergent or divergent. Now, let me, so let f and g be continuous functions, and f of x bigger than g of x for x bigger than or equal to a. And I guess, yeah, the book also assume that we should assume that it is bigger than 0. So these two functions are like this. Say a to infinite, so this might be f, this might be g. F, in fact, is bigger, and g is lower, from a to infinity. So from a to infinity, this one is above this one. So a, not a, let's say 1. We have a over them. So what can we say? First of all, if this upper one is finite, if the area under fx is finite, then the area under gx is finite. Because this shape is included in the other one. This shape is inside this. So the first one is this. If a to infinity fx dx is convergent, then integral from a to infinity gx dx is convergent. Okay, and well, let me write the second one and then look at them algebraically. The second one is this: if this below gx is infinite or divergent, if this area is infinite, then the upper one is also infinite, because this upper one includes this one. So if some area includes another area, and the one that it includes has infinite area, say, then the bigger one also has infinite area. So if the lower one, gx dx, is divergent, then the upper one, which is fx gx, is also fx dx is divergent. Okay. Now how? Let me erase this and show you the right way. We have this situation here. We have this situation that fx is bigger than gx, and they are both bigger than 0. So the integral of, say, from a to anything b of this thing, first of all, it is bigger than 0 because the integrand is bigger than or equal to 0. So the integral is bigger than or equal to 0. This is always less than this thing, or equal. Okay. So a is telling me, and let b go to infinity, right? That is true for any b. So it's true as b goes to infinity. So if this is finite, this should be finite, right? If this is, say, 10, this can't be 10 million, right? So if this is 10, this is finite. So as b goes to infinity, this stays finite. So this also should stay finite because it's always less than or equal to the other one. So that is in fact a, and 1. So this is 1 in fact. This finite implies this one, gives me this one. The other one is, I assume that this is infinite. As b goes to infinity, this gets larger, 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 larger. This is bigger than this. So it should also get larger and larger and larger and always bigger than this. So if this is infinite, this implies that the other one is infinite. And this is number 2. Okay, so example, let's try 1 to infinity, the one that I wrote for you, x4 plus 1 dx. You have to find something to compare with this. Let me write, say, 25 here, okay? Not 1. Or maybe I write 10 here, not 1. Anyway, whatever this is, you have to bring it down to x4 plus something. So if I have 2x4, just divide, pull that 2 out. So just let it be x4 plus something. Okay, this 1 over x4 plus 10, for example, first of all, it's bigger than 0 for x bigger than 1, and it is less than 1 over x4. Why? Because the denominator is always bigger than the denominator here. It is x4 plus something, so the denominator, but algebraically speaking, since these two are all positive, we can say that x4 is in fact less than x4 plus 10, and since they are positive, when I flip them, this is x4 over 1, this over 1, when I flip them, this thing changes. This one doesn't change. So that is 1 over x4 plus, say x4, just x4 will be, becomes bigger than 1 over x4 plus 10. This doesn't happen when we have negative, right? So if this is negative, this is positive, the reciprocal is also positive negative. So this happens when this happens. Therefore, this happens. And this integral is convergent. So the integral of this, let's write it. Well, 25 doesn't change anything. We can just write 25 here. So it's 25 over x4 plus 1 dx is less than 0 infinity of, say, 25 over x4 dx. Right? And this is convergent. So it implies that this is convergent. Okay? So convergent gives me convergent. Okay, so as I said, it's not easy to find this integral explicitly from a to b, but we can say that this is a convergent or divergent. We can prove that it is convergent in this case. Now, why is it important? Because eventually you might need to find this integral using some numerical method, say midpoint or midpoint rule or trapezoidal rule or Simpson or whatever. If this integral is divergent and you try to find it, you might waste computer time and the number you're finding gets larger and larger and you don't know why it's getting bigger and bigger. But if you know it is convergent, and if it gets bigger and bigger, then something is wrong with your code. But if your code is correct, then it will give you an approximate value for this thing. And that is, in fact, important when it comes to, say, numerical integration. Okay? So it becomes important in numerical integration. Convergence of certain things becomes important in not just numerical integration, in numerical mathematics and numerical analysis, which is crucial in many areas of mathematics, engineering, physics, and whatever. So studying this thing and finding out whether an integral or something is convergent, then it's important. And this is one of those, say, theorems that can tell you whether an integral is convergent or divergent. Okay, so with this thing, I guess this chapter 7 is, we finished chapter 7, and so next time I will start chapter 8. Okay, so see you next time.